Okay, hello everybody. I hope you all are doing great. And today we all welcome you to our free webinar course on structural analysis, NVH, crash, and durability. So today we'll be leading our first session out of 60, and within this 60 sessions we'll be achieving the mastery in CA in respect to the structural analysis, NVH, crash, and durability. So first of all, I would like to thank you all for supporting our community in respect to Technocraft Academy. When it comes to WhatsApp community, we have more than 200 members who has joined us, and we heartily thank each and every one of them. And when it comes to social media like Instagram, LinkedIn, and Facebook, we have around 500 community members. We heartily thank them also for supporting us. Well, let's get started with the session. Okay, so today I'll be taking you through the first session out of 60 where CA mastery begins. Let me introduce ourselves. If you're joining this session for the first time, you need to know about us, or you already joined the previous CAD session. I hope you already know about us. So in short, we provide the trainings on computer applications, spoken English, CAD 𝐂𝐀𝐄 𝐓𝐫𝐚𝐢𝐭, data analytics, and full stack development course. And we also deliver 100% placement for each and everyone who are taking the course from our side, and we'll also help them in building their resumes and prepare them for the interviews and make them the interview cleared and get the job out of it. So this is what we do currently. And if you people are looking for the job oriented corporate trainings, and the colleges and universities who are looking for the support from our side to train their students, we're always available. Please do contact us, and the contact details will be given in the next slides. Well, myself, I'm 𝐂𝐀𝐄 𝐓𝐫𝐚𝐢𝐭, Corporate Training Head at Technocraft Academy. I handle CAD 𝐂𝐀𝐄 along with public speaking, soft skill development, computer basics. Yeah, and along with this, I do handle automations and full stack development course. And data analytics course will be handled by our colleagues, and remaining courses will be handled by our colleagues. So please do contact us so that we can guide you out which course you're looking for, and we can schedule the batch accordingly, and we are ready to train you guys. Well, let's get into today's session. So why exactly we are here? So first thing, we need to know about industries to get into the market, right? Let's say this session is basically for the CA and FEA engineers who want to start their career. So for that, you need to know about the industries. The first one is the tier 3 industries, where these particular industries will provide the raw materials to the OEMs. Okay, when it comes to tier 2 industries, what they do, they provide the great parts, non-automotive parts, and the systems. Tier 1 industries, they provide sub-assemblies, automotive components, the casting components, and they will machine it, and then finally they deliver the parts to them. And finally, we have the original equipment manufacturers, where they assemble everything and they also manufacture the main components and bring the cards or industrial equipments into the market. Yeah, so these are the few examples. When it comes to tier 3, we have UMC and TSM, global example. We have NXP for tier 2 industries. When it comes to tier 1 service based industries, we have the Bosch, and they provide the components and the sub assemblies for them. And we have the Continental, we have the ZF. And when it comes to OEMs, we have the Daimler Trucks, General Motors, Toyota, Honda, Suzuki, Volkswagen, Ford, Audi, BMW. These all are the original manufacturing companies, yeah, equipment manufacturing companies. I hope you got to know about the industries, right? So now where we need to fit in. So for us, the outsourcing companies, so what exactly OEM does? In short, they try to outsource their projects. Okay, let's see here. When it comes to for example, you have a automotive company. Assume we are working with Indian based OEMs, Tata and Mahindra, for their CA activities, let's say meshing, contact definitions, okay, and all the BIW trim meshings. What they do, they outsource this. Why? Because the cost effectiveness. Let's say if they want to hire a guy, so they need to pay him more, yeah. So when it comes to outsourcing, they need to pay less and they don't need to worry about the guy who has joined that service-based company, whether he's going to resign or he's going to stay there. It doesn't matter for the OEM. Yeah, when it comes to them, if they hire one guy, he's permanent. They can't do anything. They need to invest a lot, right? Very important. The next thing is the focus on the core competences. The meshing activities and model build activities not that important for them. So the important thing them is to make the validation out of it and make the decisions and make the component manufactured is the important thing for them. Yeah, and speed and scalability. So they can focus on other important things, which leads to speed and scalability in short. So for CA engineers, outsourcing like service-based companies are the very important footprint or starting footstep, we could say. Okay, well, let's see how they are and how they are going to help us. If you're a fresher, so what exactly you can do? What are the career options you have it with respect to the domains in CA? Let's say we have the CA domains, we have the NVH, we have durability, crash, optimization, multi-body dynamics, thermal analysis, CFD. So lot are there. So what we can do is we can focus on any of the one domain and we can gain the mastery in it and get into the industries. Okay, if you're from local universities, it is quite difficult for you to get into OEMs directly. So for that, what you can do is you can join the service-based companies that I'm going to tell you later on. Well, first focus on one of the domain, that is durability. What exactly we do here? We calculate the fatigue and the durability of the component. We also check for the creep and the fracture mechanisms. So we use predominantly the Abaqus everywhere, and we can even focus on Ansys mechanical. Yeah, the physics behind this is the stress analysis, the material behavior. Okay, that's about durability analysis. We'll also see about optimization now. So what exactly we do here? So domains are the topology optimization, shape and sizing, sensitivity analysis, and multi-objective optimization. So with this, what we do, we try to optimize the component. Let's say assume one component, knuckle or any of the medium scale industry component is weighing XX grams or kg, let's say 8.5 kg. And I would like to minimize the mass and also improve the performance of the component. What we can do in that case, we can run the topology optimization, get the load parts out of it, and re-realize into CAD and just make the model with minimized mass and with improved performance. Okay, let's say 8.5 kg is there. I have reduced the mass up to 1 kg, and also the performance is improved. If you provide the component, the market will be very happy and the OEM will be also very happy because the cost saving will be there in respect to the manufacturing and the material. Let's say if you are going to minimize the mass for one component, that component will be implemented in lakhs of cars or lakhs of medium scale industry components, and that is going to save a lot of money for them. Okay, very important. Now we'll see about crash. When it comes to crash, this is the biggest domain ever and very popular, and job openings also are there, but getting into this is quite difficult. you need to have a lot of experience into that, but this experience you're not going to get outside. You need to struggle a lot to gain the experience. Yeah, for example, we have the front impact test, we have the rear car impact test, side impact, we have the bumper impact, side impact, occupant safety, roof impact, where we had one case, right, the Volvo car which was unable to withstand the lorry truck which has fallen on it. So it's a misfortune, we could say. The whole family has died on the spot. Okay, dead on the spot. So for that we do these all the analysis and try to make our car better, which is acceptable in the market, and from that we get the ratings, right? 5-star rating and NCAP ratings, we know, right? So this is what we do it here. Similarly, you can just check for all the domains and try to get the master in it. Definitely you'll get the job. Well, so now if you're a fresher, I would like to suggest you what you can do. Let's say I don't know anything and I'm having some experience in CE. I know the basics and I'm into the CAD domain and I would like to get into CE. If you are in this stage, what you can do is, first, set a strategy, know about yourself first, okay, and just try to set a basic framework. Let's assume you don't know anything about FEA. What do you need to do? You need to explore the fundamentals of SOM and DOM, yeah, and then know about each and everything which is needed for the FEA, CAE, yeah. Let's see now, for example, what are the career options. Let's say the first one is the CAE modeler. So if you don't know about the fundamentals basics better, just get to know about the tool, that is Ansys and HyperWorks, Altair HyperWorks meshing tool. So Ansys and HyperMesh preprocessor, these are the preprocessors actually, but Altair HyperWorks has a lot of things, but they do have the meshing capabilities. Both are very predominantly used in all the OEMs and automotive companies. So in that, what we do, we try to mesh the component, we define the contacts, we also try to morph the component as per the need. Yeah. So what you can do is you can do these activities, but if you don't know this also, you need to join the training institute. But currently in the market, the training institutes are not that predominant and they are going to teach you the basics. That is not sufficient, and if you want to learn Ansys and HyperWorks perfectly, you might need to reach out the BetaC and Altair training providers directly, authorized training centers, but the charges might be more, might be up to 1 lakh, so you need to compromise for that. Or else you can refer the YouTubes like us who are going to provide you the well-versed content, so that you can refer that and you can gain your experience in it. So along with this, you can even approach resellers where they can train you on this. Well, now what would be the package you can expect from it? So you can achieve up to 3 to 6 LPA if you're freshers. It is on an average 3 lakhs. To be frank, it is 3. It is even less than that. You can even achieve 18,000 rupees or 20, 25, 30. In the current market, this is what you can achieve. Well, so tools, as I said, Ansys, Beta, that is, and then Altair, HyperMesh, you need to know for the CA modeling. First option it is, okay. The second option, alternative option, is what you can do is become a CA modeler. Along with this, focus on analysis. So what exactly you can focus on? You can focus on any of the domain, NVH, crash or durability, gain the experience, refer the YouTubes, or join these training centers where they will try to give you the exact corporate based trainings, and then that knowledge will help you out to get into this. One more important thing is, if you are a CA modeler, if you know the basics of NVH, durability, crash and optimization, definitely they will hire you. Okay, where do you find this content? Very important. If you are not going to get it from the training centers which are available in the market, do refer the YouTubes or the contents which are made from the 𝐵 and Alter HyperWorks. If they're not, please don't waste your money with the what I can say, the trainers or the training providers like the CAD Center, and there are other training centers who are simply taking the money in the form of business, and they are just teaching the basics that is just a trash. Okay, that is what I could just suggest you guys. Well, so what about the package for this? You can expect up to 6 to 8 LPA, 40, 50 or 60,000. If you have this knowledge also, you can even achieve 65,000 to 70 also. Yeah, on an average I could assume it is 6 lakh per annum. You can have it. If you're a fresher or if you have slight experience, 2 to 3 years, this is what you can have it. So to have this analysis, you need to know about the Ansys, Alestyna, Abaqus, OptiStruct radius. Okay, even the OptiStruct also is important. This is the second option I could provide you guys. The third and the very important option is the resellers you can join. Software resellers like the SolidWorks, 𝐵, Alter HyperWorks, Dassault System, and Autodesk. Okay, you join them as a technical support or a pre-sales engineer. Okay, and then what exactly you could do is you can explore all the industries, you can meet them, you can get to know about their requirement, you can help them know about their pains, solve their issues, implement that particular issues in the software. Okay, this is very important. So what I'm telling is, this is what I did. I was into a reseller before, and then I gained a knowledge. I think more than 2 to 3,000 companies I was working with, supporting, training, giving the services. Yeah, and then this helped me to gain the knowledge on all the CE tools, and then yeah, this was the, what I can say, the backbone for me. Similarly, I would suggest if you are a fresher, better join any of the training institutes, sorry, resellers, that is what we call it, then gain the experience and try to switch later on. What will be the package? So initially you can even have up to 5 LP average, and then 2 to 3 is the for the freshers. Yeah, tools you need to know, that is Ansys, Abaqus, SolidWorks, Ansys, and Alter HyperMesh. This is the third and important suggestion I could give. Now, if you want to become a CA modeler, what are all the things you need to know? So for that, this is what the skills needed. As I said, the package is 4.5 LPA for the beginners, or 3 you can consider. Basic fundamentals you need to know. Yeah, modeling tasks like meshing, morphing, full vehicle integration, creating the includes, okay, meshing the trims, properties and material assignment, sheet metal component meshing, and the quality checks for the mesh. For that, you need to be good at Ansys, Alter HyperMesh for the automotive industries. If you want to go for the small scale industries and the medium scale industries, I would also recommend Ansys. Yeah. Next, CE analyst and CE automation analyst. This is the one of the, what I could say, the topmost position we could see. You will be joining as a CA engineer, and then you will be promoted to a senior CA engineer, and then you will be under automation after that. Once you know the tool, everything, you can do the automation scripting. The package you could assume, if you are into OEMs directly, you might achieve up to 15 to 20 LPA directly. Okay, and then later on the package might increase drastically. Next, the skills required. As I told, you need to know about any of the domain, NVH, durability, or crash. You need to know about the model, dynamic, and the static structural analysis and validation. Very important thing is the automation, model debugging skills, optimization, or coding. Okay, anything is fine. If you are perfect in NVH, that is sufficient. And very important thing is the communication skills. You need to develop that. If you don't have the communication skills, you are not even qualified for this role, because you need to deal with the counterparts. They might be from foreign countries, they prefer English. Yeah, so you need to present and make them convinced. That is important. So tools known: OptiStruct, Abaqus, and then radius, Alter, OptiStruct, and then Nastran. And if you want to become a CA engineer in the beginning, you don't need to know about the Python coding and automation. So once you're into CA engineer, you need to try to get into the coding also later stages, because you need to get the promotions and all. So you need to know about the Python scripting and implement it into any of the tool, and so that that particular process will be automated. Okay, I hope it is clear for you guys. So this is what the roadmap for the CA engineers, starting from the scratch. Now later on you'll be under the lead positions. You can lead a team, and then the package will increase, and then you'll be a manager, and then you'll be again different positions like L5 technical if you're into T5, and then E4, L4, okay, sorry, E4, and then E3, E2, like that. So you'll be having a lot of designations, but up to T6 and T7 you'll be under a lead or senior C analyst. Like this, your profile will be gradually upgraded. I hope this is clear for you guys. So this is what it is. In short, if you don't know anything, start from the scratch, do the modeling activities, or else join the resellers and know about all the basics, and then also explore all the tools and the domains in which crash orderability or optimization. Then get into this market. Now that is what we had seen. Now how the market is, what and all you need to know. Now how do we start? So for that, I try to summarize the contents and brought you the contents so that you can refer them and try to analyze it and implement it to your day-to-day activities. If you're a fresher, well and good. If you're experienced, try to refer my videos so that you can gain the experience and get the job out of it. Let's start with the basic from the scratch. The history of FEM. The first and foremost thing is, in 1956, Turner, Clough, Martin and Top has published a paper that is stiffness and deflection analysis of the complex structures. This is considered as the birth of finite element methods. After this, the term finite element was coined by Reliclow. Okay, and during this particular 1960 only, the program was invented, that is Nastran, to solve these problems. After this, what happened? There's a Corin's approach where exactly we divides the domain into finite triangles, and then they solve it in the form of the partial differential equations for the torsion of the cylinders in the beginning. Later on, this was revolutionary for others. They use this method and they try to define the partial differential equations for large bodies like the Lord Rayleigh and then Walter-Ritz for model analysis, and and Boris Galerkin's method, weighted residual method, also will come into picture. Yep. And then later on, it gone and gone. Finally, this particular method is being generalized for all the numerical methods for the physics like the engineering disciplines, structural, electromagnetism, heat transfer, and then fluid dynamics. Yeah, this is about the history. I hope it is clear. Next, the simple question, what is FEM? They will ask, what is FEA? In short, you could see the definition. This particular finite element analysis is increasingly popular method used to solve the problems in static structural analysis, dynamic, vibration, fluid flow, heat transfer, and many more other industries. In short, in finite element analysis, we try to solve the problems related to all these fields. Yeah. When it comes to classic analysis, we consider a differential element and develop the governing equations. In short, partial differential equations we try to generate. And then, for example, when it comes to real life problems, it is very difficult to obtain the exact solution for the geometries which has the complex equations, right? So now that also has the boundary conditions. To solve them, it is impossible task, right? Now, in the finite element methods, what we can do is we can simplify this one by using the approximate solutions. Okay, we try to provide the approximate solutions in the form of the partial differential equations, and that partial differential equations will be converted into the algebraic equations in the algorithms like the tools, and then next they can be easily solved. Yeah, this is what the FEA is in short. Clear? Now, finite element formulation, how exactly it is formulated. For example, so let's say usually the solution for the field variable satisfying both the boundary conditions and the differential equation is unknown, right? For example, we don't know the boundary conditions. The boundary conditions also unknown if you have the complex geometry, and the differential equations also we don't know which one we need to use. As per the boundary condition, we need to define this. Okay, so what we do, we try to define the trail function, trail solution for this. So where this trail solution will help us to formulate the boundary conditions which are satisfied. Okay, I'll show you that one later on. Now this trail solution assumed does not satisfy the differential equations exactly. There will be a slight error in satisfying the differential equation. So that error, how do we satisfy? So for that, the term comes is the weighted residual sum. So where we try to have a constant which will help us to make the entire domain rendered to or equivalent to 0. Okay, very important. So we'll see this one later also. Next, what we do, once we have this one, we try to discretize the model into several segments called finite elements, and then we use the piecewise continuous trail functions to solve it. Let's see that one. Now, let's say when we have the trail function for each and every elements, so what we call them as a shape function. What exactly the shape function is? Okay, these shape functions are defined in the form of the interpolation functions, where these exactly implemented in the elements on each and every points. Key, we call it as nodes. Assume we have the 1D element, these are the nodes, right? Here we define the shape functions and we formulate the trail functions. For 2D, you could see these are the first order elements, only 3 elements for the trio. We have the 6 for the second order. Similarly for the quad, we have 4, and here it is 4 plus 4, 8 and 9. Yeah. Well, for these are the 3D elements, we have the tetrahedral, hexahedral and the quadrilateral. Okay, first order and the second order. So for these, on all the nodes, we try to extract the results that we try to simplify the shape function, which we call it as. Yeah. Next, so now with these shape functions, to have the error eliminated, we use the weighted sum of the domain. Okay, it is computed for each and every element, and later we sum of all the elements, and then we get the weighted residual sum of for the entire domain. Okay, for example, if you consider one of the element will be having the XYZ stresses, if you want to extract it, right? XYZ also you need to extract stress strains, we call it sigma XX, right? Sigma XY, sigma YZ, and then along Y, along Z also we need to extract, right? So all these, on all the elements, these many tensors will be there. How do we need to get one equivalent value? That also I'll explain in the later session, means in later slides also. Let's see now how we can get the weighted residuals out of it. Now, once we generate this weighted residuals in the form of the stiffness matrix, we call it. Okay, so you can see here for all the elements using the shape functions, and we have elemental level characteristic matrix. So once we have the shape functions, with the shape functions we'll be generating the stiffness matrix. To solve this, we have the different tools. In that we have the algorithms programmed to solve them. Okay, for example, we have Ansys, Abaqus, okay, Nastran, OptiStruct, likewise, to solve it and get the results and post-process it. Now, so what exactly a user can do is, user can choose the discretized model in his domain, variety of the different finite elements. The program sets up the characteristic matrix for each element. Okay, try to set up the stiffness matrix, and then sum of them of the entire element, finite element mesh, to set up and solve the system level equations. In short, it will take this equation, try to set up the stiffness matrix on the entire model, and then it will solve the results, and you can use in the form of displacement, stress and the strains. First extraction will be displacement, and then it later will be converted into the stress, strain and the factor of safety, and for a nonlinear, different things. Yeah. So this is how the finite element formulation will happen. I hope it is clear. If it is not clear, please refer this video again. It will be understandable for you. And if it is not even understandable, please refer other YouTube videos or the books before getting into this. Might be hectic, might be for you it is too much loaded or overloaded, or it is not going into the head, it is over the head also, above the head also it will go. Don't worry about it. Try to refer again and again. Definitely you might get slight knowledge about it, so that you can later on increase your in-depth knowledge with this small amount of knowledge also. Next, so the same formulations, the same steps will be used for other domains also, for the structural, heat transfer, CFD, electromagnetic fields also. Yeah, they'll also try to approximate the differential equations, not only the partial. There will be different types of differential equations, and then from that they'll get the results by using the different algorithm programs. Now we need to know about the process, right? What exactly we do in the FEM. Even in the interviews they will definitely ask you what is FEM, so what exactly you do in FEM. So explain that with an example they'll ask. If that is the question, you will be lucky, because I'll be trying to explain you here, so you can explain the same thing there also. Let's say if we have a assume component, if the interviewer asks, or if you want to explain to someone else, if you're facing the interview, you can, instead of taking the rectangular block, you can consider any of the automotive industry component, a knuckle or a crank or anything, a shaft, whatever you can consider. Assume I have a rectangular component, or I have a component. So what we do first is we assign the material properties. In the material properties, the mainly we take it is the Young's modulus. You need to know about Young's modulus, what it is, what is elastic limit, okay, what is ultimate strength, what is Hooke's law, okay, everything you should know. When it comes to Poisson's ratio, what is this, and density, okay. Now once you assign the material properties, what do? We try to apply the boundary conditions. So boundary condition depends upon the requirement. It is very simple here. You can even have the complex boundary conditions, the fixtures and the loadings, okay, we do apply here. After that we discretize the model into the small elements, okay. For small elements, might be a trias, might be tetrahedral, hexahedral in the form of 3D. In 2D it is tri elements or the quad elements, okay. This is complete your quad elements you can consider, okay. Now what we do, we try to extract the shape function for each and every element. So you could see here we do the calculation for each and every elements. On the nodes we try to define the stiffness matrix, okay, and then from that we get the stiffness matrix out of it and we try to solve it. Just give this to the any of the algorithm, and this particular stiffness matrix will be taken into account and formulated, and we will solve it to extract the results in the form of the displacements. Then we get the results in the form of displacement when we post process it again by using this displacement into stress, strain, and the factor of safety. Yeah, this is what the entire process is. They might even ask you what is stress, strain, and the factor of safety later also. Yeah, I hope this is clear. This is known as the divide and conquer rule, okay. Okay, now we'll see about finite element formulation from the general governing equation. So what are the equations initially we had it, and what is currently or regularly used upon? First one is the direct method, we have the variational method, we have the Galerkin's weighted residual method. So from these three, this is very important, the Galerkin's weighted residual method. We'll see how it is and why it is. When it comes to direct method, it is a strong form, but this equation is not widely used because this is simple and it is quite difficult to utilize for the complex components. In short, it is used for the Excel problems. Yeah, EI derivative of 4 of x into qx plus boundary conditions. This is what we have the direct method. Now when it comes to variational method and the Galerkin's weighted residual method, these two are the weak forms, okay, weak forms of integrals. We use the integration here, try to solve the problems. So now these are the again approximate solutions. We try to make equilibrium equations out of it, and this is easier to solve. Now when it comes to variational method, this will work on the principle of minimum potential energy. For example, we have the potential energy which is equal to strain energy plus work potential. Okay, you can see here strain energy is the deformation stored in the structure, and the work potential is the negative of the work done by the external forces. Okay, this is what the formula is: total energy, strain energy plus potential energy of the external loads. Okay, very important is this one. So this is what is currently we are using it, that is Galerkin's weighted residual function, that is weighted residual method. So what we do here is, this method is very popular and powerful also. So what exactly it does is, it will try to solve the differential equations. So by using the piecewise trail function approximation, okay, it will try to solve the weak forms of the equations and give us the stiffness matrix out of it. Let's see how it is done. Okay, now let us consider the simple example. So this is the total domain, okay, where we need to do the calculation, and this is L is the boundary. Okay, now this is what I try to explain. Okay, while satisfying the prescribed boundary condition L, we need to take this as a scenario. We have the fixtures and the force applied. We need to do the calculations into the domain. Now assume we need to take a trail solution. For example, this is what the trail solution is. Okay, Fourier series and all, if you could able to go through into mathematics, you'll understand what is it. Okay, f of x is equal to c0 plus c1x plus c2x square and so on. Okay, in general the function so assumed will be satisfy neither differential equation, correct, with the domain or nor with the boundary conditions. Okay, in general this is not going to satisfy for this. Now what we do, we substitute assumed functions in the differential equations and the boundary conditions of the problem. Okay, we try to define the boundary conditions and the differential equations. For example, to find the error, we assume residual domain and the boundary residual. Okay, we take these as the residuals. Again, we take as a certain constants. Okay, now determine the unknown parameters here again. So c0, c1, c2 are the unknown. Okay, in assumed functions in such a way that we make these residuals as low. We need to calculate these so that the residuals will become near to 0 in short. Yeah. Now in Galerkin's weighted residual method, the unknown field variable is u. Okay, we consider that and we approximate the solution in the form of u, same, which is this equation, which is equal to, this is what the equation we used, right, trail function. So ih is equal to 1 up to n ci and I, where ci is the independent coefficient which is determined by the weighted residual process. Okay, this is the constant we consider, and ni is the pre-selected such that displacement satisfy all the prescribed boundary condition. So n we are pre-selecting, ih is equal to 1 up to n. Now we consider R is the xyz, the domain residual. Okay, now what we can do is, this equation we can rewrite as, okay, weighted residual R is equal to 0. So when I is equal to 1 to n, if we write it, where wih is equal to ni, so we consider this as n. So this is what we get it. We try to make this equation as 0. Okay, now considering the general weighted residual statement, we try to again simplify this by using the equations. Okay, this is the equation, general weighted residual statement, and trail function, if we use it, this is what it becomes: integral of 0 to L, and assume initial displacement is 0 and weighted residual is also 0. Now with that, we take the partial differential equation for the axial load. If we consider this equation, okay, AE which is equal to d square u by dx square plus k which is equal to 0, we try to feed this here. If we solve this one, integral of 0 to L, we consider AE. This is what the derivative we have considered, du by dx plus dw by dx. Okay, then this is how it will be written. Okay, you can see we remove this, and finally we have this equations, AE by du square by dx square plus ax which is equal to 0. This is the equation we assume. Okay, now this is what the equation from where it came. Now you wanted to check it. This is the differential equation for the varying load. Okay, linearly varying load. Now we have this equation here. Let's say that is what I'm telling. We take for one element. We need to solve the shape function for this. On each and every nodes, we try to extract the stiffness matrix, and we combine this one to get one elemental stiffness matrix. We combine these all the elemental stiffness matrices. Now if you want to consider only one, we need to solve for the displacement. So if you consider du displacement at xy, if I consider, now here we have the 4 displacement needs to be extracted, so u1 to u4. So this is what we write it here, u of xy which is equal to here, this is what we write it. Then finally this is what we commit, or else that is n plus u. Okay, n is the constant, u is the displacement. This is how we write it directly. If you substitute this one here in the equation, du dw by a into du by dx by dw by dx 0 to L, this is what it becomes. Okay, you can see this is the K stiffness matrix. We have the displacement plus the load. Okay, now for example, this might be for you quite complicated to understand again. So if you want to go through this one, so you might need to refer the books, and then you'll understand how this can be formulated again. Yeah. If you solve this, you will get this one. Now, for example, we have the stiffness matrix. So to solve particular stiffness matrix problems, so if we consider a simple example which is axially loaded, L is the length, and the P and the Px plus delta x are the loads, forces applied here. Okay, u1 and u2 are the displacements. If I consider all the equations, stress, strain and Hooke's law, stress is equal to force per unit area. When it comes to strain, change in length to the original length. Hooke's law, if you want to define, when it comes to elastic limit, considering, okay, if your component is under the elastic limit, stress is directly proportional to strain. If the strain is doubled, stress will also get doubled. So this is the proportionality constant, we call it, yeah, E. Now if we try to solve the equations, so let's say load which is equal to area into stress, when it is stress is the Young's modulus into E, change in length to the original length, AE by this one, u02 and this one. Now if you want to just solve this one equation, so how do you feed it? Positive and negative, right? So negative is the minus px, correct? Positive is the p of delta x plus p plus integral of force x plus delta x, we add it. Yeah, we solve it for the 0. When it comes to 0, delta x tends to 0, we need to solve it for this. So p is the phi of delta x minus p of x. So I'm just removing the delta x here, divided by delta x here, f which is here. So if I take f and here derivative of p, okay, by dx, correct? So here, yeah, delta x will become 0, and then here we try to solve for the derivative of p. Now when it comes to this equation, when we have the p, if you feed it here, ae by u du by dx plus f, in short, stiffness matrix into displacement which is equal to force. Yeah, this is how the equation comes for the axially loaded elastic bar. For example, we have this one here. For example, let's say yield stress of the component is 300 megapascal, and we have the strain. Change in relative version length is 0.0015. Okay, then if you solve this one, you want to extract the Young's modulus. This is the formula, Young's modulus, which is equal to stress by strain. If you divide this, 15 ones are 15 twos are. Okay, and then you need to bring this one here. This will become 200 gigapascal. Okay, so in short, this is how we use these all the mechanical properties to solve the equations. Now, general equilibrium equation. So for example, you could see we have this equation where M is the mass matrix, U double dot is the acceleration, B is the damping matrix, U dot is the velocity vector, K is the stiffness matrix, and U is the displacement, P of T is the applied load. If you want to solve the results for the static analysis, where the mass matrix and the damping will become 0, acceleration and velocity will not be there for that, and then the equation will become stiffness matrix into displacement, which is equal to P. Similarly for the buckling, this is what the equation is, where lambda is the eigenvalue, where phi is the eigenvector. Okay, and for the vibration, this is what the equation is, K minus lambda to M, which is equal to phi eigenvector, which is equal to 0. Okay, for the transient analysis, the same equation we use it, where velocity, acceleration, displacement, everything will be taken into account, and try to solve the linear, non-linear, dynamic analysis. Yeah, clear, right? So this is the general equilibrium equation. So you need to know this one and try to explain it. Now, how do we solve the engineering problems? In short, if you are fresher, you need to know we use the analytical method, numerical method, and the experimental methods. Crash test we do it right on the components. Numerical methods we use the softwares. So in the numerical types we have the FEM, BEM, FVM, and the differential method. In short, in FEM we try to extract result for each and every nodes, and in the boundary we try to extract the results on the boundary and try to interpret the results on the elements. Heat transfer we do it here. Next, for the volume we use the Navier-Stokes equation. It is a different domain again. You need to know about the laminar flow, turbulent flow, what is coefficient of lift, drag, viscosity. Okay, a lot of things will come under this, so a vast domain. When it comes to finite difference method, we try to use the Taylor series method and try to extract the results. Yeah, now in CAE what and all will come. So first is the FEA, structural analysis, then we have the CFD, multi-body dynamics, thermodynamics, and then the electromagnetic analysis. Yeah, and then the optimization. These all are the CAE domains, types also you can say. You can achieve any of the 6 domains, mastery you can achieve it, and then you can become an expert and get the job in all these fields. Yeah. Now, what about the types of FEA? So we just see in the CAE, right? In FEA what and all we have it. We have the static analysis, we have the dynamic analysis, we have the model analysis, buckling, and the fatigue analysis. In buckling we try to check how the component is going to buckle and how do we need to optimize it. In the model analysis we try to extract the results for the mode shapes and extract the results at the certain frequencies, how the component is behaving and what would be the mode shapes, and with that we try to check the resonance. The dynamic analysis with respect to the vibration, how the component will be behaving for the particular natural frequency, what we should do to avoid the resonance, yeah, and also the damping, how we need to apply. Static analysis, most of the things you know, apply the loads and extract the results, whether it is failing or not, you need to predict it and post-process the results. Next thing is the fatigue, for the repetitive loads, how the component will behave, so how much lifespan that particular component will be having it, and analyze it, and where are the weak points, where will the crack propagation, so test it, optimize it. Then the heat transfer, finally in the form of the temperature distribution and heat flux you'll get the results. Yeah, finally we have the nonlinear analysis, where we need to define the nonlinear material, geometric nonlinearity, and try to extract the results in the plastic region and check the material failure and try to give the solutions accordingly. Yeah, This is very costly one. You need to have a lot of exposure for this. Now, in the linear and the non-linear dynamics, what are the types? One is the modal analysis, the response spectrum, time history, harmonic, random vibration. These all will be used in automotive and the medium scale industries. Please go through all the definitions. If you want to explore more, try to refer my previous videos. It is already available in the playlist and it will be explained. Due to time constraint, I'll just try to proceed further. Now, this is important, guys. This chart will help you to understand what is linear and non-linear, dynamic and normal analysis. For example, linear will be linear static and the linear dynamic. Okay, so in linear static, again we have the implicit. So where we try to solve it for the small deformations near to the elastic regions. For example, we have the strength analysis, preloading, gravity loading. Now when it comes to non-linear, explicit analysis, it will consider material non-linearity, geometric non-linearity, contact non-linearities also. It will run the results for the shorter events and the large deformation will be expected out of it. And where it is used? Due to the crash analysis, drop test, explosions, bird strike, everything. Yeah, I hope this is clear for you guys. What is the difference between implicit and explicit and where exactly it lies? In short, to get to know about this, in short, you have the structural analysis where static loads will be applied. This is the explicit where we do the impact, large crash tests and all. In between these two, we have the implicit. For example, if you want to do the metal forming analysis, so we are not completely destroying the components. We are just trying to deform the shape of it and achieve the deformed shape after elastic limit in the plastic region until a certain particular point we can extend the material. So this is, we call it as quasi-static, where the metal forming and all takes place. Quasi-static we call it as. For example, caps. Okay, if you want to rotate it and you want to just there will be some knobs will be given, right? If you just tilt the bottle cap more, and then that barrier will be broken and you can use it. A kind of analysis we do it here. And the sheet metal forming analysis also will come under the quasi-static. Now, how exactly the quasi-static will be done? For example, if you consider the dynamic and the impact analysis, we define a direct load 1, but in quasi-static we try to gradually increase 0.1, 0.2, 0.3, 0.9 and 1 unit load we apply, and then it will be straight. In the sheet metal forming also, we gradually apply the load and we make it bend, and then we apply the full load. Likewise, we do the quasi-static simulation here. It's clear, right? Now, these are the important things, the mechanical properties you need to know. That is the yield strength, where it lies here, yield point. It is under the proportional limit. Okay. So you could see it is already written elastic behavior, maximum tensile strength where the material can handle before the permanent failure. When it comes to ultimate strengths before the failure, what would be the ultimate stress it can handle? Okay. What is the fracture point? This is the stress at the failure point. Stiffness is this region also. In short, the component resists the elastic deformation when it is applied, when the load is applied. What is hardness? We did the CRP test, right, to check the indentation hardness of the component. In short, localized surface deformation. Resistance to the localized surface deformation, we call it as the resistance. Hardness. Yeah. For example, for different materials we have the yield strength. So these are the values here. You need to know. So when it comes to steel, I could assume it is 230 megapascal is the maximum stress it can handle under the elastic limit. Likewise, these are the yield strengths to remember. Yeah. Now, let's move on to the next slide. This stress strain curves for the different materials. For brittle, the small strain at the fracture, only a small change in length will leads to complete failure. But in ductile metal, it will try to have the large strain. It will try to extend. After elastic limit there will be a plastic region, and then after a certain load application it will fail. This is what it is trying to explain. We have the stress, strain. From 0 to A is the proportional limit. Hooke's level satisfy here. And then after this we have the elastic limit. Up to here material can go and it can again regain its original shape. But if the elastic limit crosses, if it is close to yield point, there will be a deformation. So this is what the plastic region we call it. Up to here we can do the quasi-static. And then after this we have the ultimate tensile strength, where it will exactly have the maximum load, and then it will fail at this point. Okay, here it is the elastic region, this is the plastic region. Now with the different types of materials, the elastic material for the static analysis, plastic for the non-linear and dynamic, brittle materials to do the brittle material analysis, elastomers also we have it, okay, which will have the rubber and all we call it as. Yeah, different types of materials. Isotropic, most predominantly used in the market for all the analysis, automotive and the medium scale industries, cast iron, glass, diamond, everything. Orthotropic, the material is orthotropic if its mechanical thermal properties are unique and independent of 3 dimension. The directions is not at all matter for this. For example, we have the crystals, rolled metals. So here all the directions, the mechanical properties will be same, but here it is not, it is independent. Here it is dependent on the direction. For example, plywood, if rubber, if you consider along one direction only, it is fine, but if you take the loads along other directions, it is not, right? Likewise. Now material properties needed, very important. They'll ask what are the material properties needed for the different types of analysis. When it comes to static analysis, we need Young's modulus, Poisson's ratio, and the mass density. Yeah. Now when it comes to non-linear, we need dynamic and the contact. We need these all. Okay, Young's modulus, Poisson's ratio, mass density. For linear dynamic, we need everything. For the frequency model analysis, Poisson's ratio, mass density is also necessary. Young's modulus is also necessary. For fatigue, very important is the stress versus number of cycles curve. Yeah, and the fatigue life curve we need it. Yeah, this is very important, guys. The stresses. So what are normal, shear, principal and equivalent stress? We'll try to understand this. First thing is the normal stress. When it comes to a stress tensor, you could see, if you consider a particular plane, assume this is x plane, we have the sigma xx, correct? Sigma xy, sigma xz, y same, sigma yy, sigma xy shear, sigma yz again shear. This is axial, sigma zz, these two are the shear. So if you want to go for the normal stress, sigma xx, yy and the zz are the normal stress, x, y, z. When it comes to shear, sidewise are the shear. Okay, this is how we write it as the tensors. Okay, sigma xx, sigma yy, sigma zz. Likewise here, these are the normal stress, this is the shear stress, triangular it is written. Why I'm trying to explain this is, when it comes to a particular component, we have all the 4 nodes, we need to use the weighted residual for this. In short, we need to have one particular equivalent stress out of it. We cannot have all things, right? So how do we do that? For example, when it comes to ductile material, it will fail for the shear stress. Okay, you need to rotate, it will fail like this, but when it comes to brittle, it will fail at the normal stress. Okay, now what is exactly equivalent stress is? We gonna have the results in the form of the one minus stress, right? This is what we do here. What we do, so we try to evaluate all the stress tensors and give one equivalent stress out of it. So this is why we try to use the 1 minus equivalent stress to evaluate the results, okay, for the ductile materials. Okay, I hope this is very clear for you people. So what are the stress tensors. What is normal stress? What is shear stress? Yeah, what is equivalent stress? Now, very important thing is this: the difference between linear and nonlinear analysis. When it comes to linear analysis, relationship between applied force and the response is exactly proportional. For example, if we have 1 meter deformation with respect to 10 Newton load, if you want to have the 2 meter extension, you need to apply 20 Newton load. So in short, the change in length is directly proportional to the applied load. Correct? Now this means the stiffness will be same for entire process. You don't need to change it. For all the linear static analysis, stiffness remains the constant. In short, if you once you calculate, that is sufficient. Now, when it comes to non-linear analysis like forging, stamping, crash, for each and every point, stiffness will vary. You can see here for the linear, it is constant. It is proportional, but here it is not. So how do we solve it? For that, for each and every time step, for the displacement, let's say you have applied the load, and then here you need to calculate the stiffness matrix and you need to have the results out of it. And then from this one, again you need to get this. Similarly, you need to solve for all the time span. So for that, this particular non-linear analysis is very expensive and also time consuming. You need to remember that. Okay. Well, so this is about the linear and non-linear analysis. I think, yeah, so this is all the basics which we had covered today. So we had just gone through what exactly a fresher and the less experienced or a 1 or 2 years experienced guy should decide his career. If they really wanted to get into the CA field, how they need to start their career. We have given the choice to them. They can choose it. They can learn the tools required. Then we also try to explain the basics of FEA, what and all it is needed. And then in future sessions, we'll be covering the basics of structural analysis, and then we'll focus on the durability, NVH, and crash domains. Yeah, so one more important thing is, if you haven't subscribed this channel, if you're watching this video, please do subscribe our YouTube channel so that we can upload the latest video so that you can have the updates on it. And also important thing is the WhatsApp community which we had built. Please try to join it so that you can get all the latest updates and the job openings also. Yeah, and please do follow us on LinkedIn, Facebook, and Instagram, most of the social media platforms, so that it is helpful for us to help many of the people and the students or the engineers to help them to build their career. So this is what we request, and please don't forget to watch our videos and try to support us to generate more and more contents. If you have any doubts, please do contact us, or if you are looking for any of the trainings or university student trainings, please do call us and we'll support you guys. So these webinars will be every weekend, Sunday we'll arrange it. It is completely free of cost, and if you want to grab the training within 1 month or couple of months or 4 or 5 months, so we'll also provide the personalized trainings. If you're looking for that, please do contact us on the given number so that we can help you out with the corporate trainers also. Yeah, that's all from this session. Thank you all for joining. See you in the next session. Bye everyone. Have a great day.